Thanks, HP, for the introduction. Hi, everyone. My name is Ibrahim. As HP has said, I'm one of HP's students in the computing program, data science, and emphasis, Boise State University. So today, we are going to be talking. Hello? Hello? Is it better? Appreciate it. Hello? Hello? Hi? Hi, everyone. Okay. Is it better? Can you hear me? Okay. So today we will be talking about machine learning, and then the objective of this tutorial is understanding the goals and the main concepts of machine learning, to prepare a SnowEx dataset for machine learning, to understand the fundamental type and techniques of machine learning, to implement machine learning with a SnowEx dataset, and then how to deploy a machine learning model. So while I give the tutorial, if you have a question, feel free to let me know, and then I'll answer the questions. So we'll start by defining what machine learning is. There are many definitions out there, and it could be overwhelming, but for this tutorial, we are going to, when we say machine learning, what we simply mean is building algorithms or computer models using data. So we'll keep it simple that way. And then the goal of machine learning is to use these trained computer models to make decisions. So that is what we do in machine learning. There's a more general definition that says machine learning is a field of study that gives the computer the ability to learn without being explicitly programmed. And this definition dates back to 1959. However, this definition can be a little bit confusing, where it says you are not explicitly programming the computer, but all we do is actually program. So how do we differentiate between machine learning and programming? However, it is worth mentioning that machine learning has great successes, such as self-driving cars, image recognition, spam detectors, handwritten digits, to mention but a few. So let's start by motivating an example, a binary example. Let's assume I want to build a model that is going to return one if a number I enter is prime and zero otherwise. So now let's try to form this problem mathematically using some kind of equation. So for now, let's assume y is equals to f of x, a very simple model. And what our y is actually the outcome. That is what we predict, whether 1 or 0. What our x is whatever we input, which is the number. And what f is actually the function that gets the job done. That is something that looks into what you put in and maps it to either 1 or 0. So if we are going to solve this problem using classical programming, all we have to do is to find a rule such that we know if a number is prime or not. So which implies that we are going to code, or we are going to hard code the rule and tell the computer, oh, if a number can only be divided by 1 and itself, then return 1, otherwise return 0. So this is what we do in classical programming. However, in machine learning, what we actually do is we give the computer some answers, give it some inputs, and we leave computer to learn the rules for mapping the input to the output. So this is what we do in machine learning. In classical programming, we have the rule, we have the data, we do the programming, then the computer gives us the answer. However, in machine learning, we have the data, we have some answers, and we let the machine learn the rule itself. So this is what we call machine learning. So it is worth mentioning that machine learning is useful when the function cannot be programmed. So just this simple example I did now, you don't want to solve that using machine learning because we know the rules. But if you don't know the rule, that is where machine learning comes in. So another exception to that is at times we know the rule, but we don't have, we are not able to get enough data, just like we know how to get SWE if we have the density, we have the depth, but this density is not available in all cases, so we have to use machine learning. So this is an exception where you actually know the rule, but you have to use machine learning to do the mapping. So for this tutorial, we will be using a SnowEx data set. We'll be using the SnowEx data set for this tutorial. Okay, we'll be using the SnowEx data set for this tutorial. And then a little bit of background about the data. The features in this data are the observations from L-band INSAR in the 2017 Grand Mesa campaign. And then the outputs, which we'll be predicting today, is the total snow depth from the airborne LiDAR. And Naheem has done a great job explaining what LiDAR is for us yesterday. So for now, we are going to have 4 input variables, and then we have an outcome we want to predict. So we have phase, coherence, amplitude, and incidence angle, and then we have the outcome to be snow depth. So, and our goal is to use the data to learn the computer model F. Recall that we represent the computer model with F. So now our goal is to learn the rule, which is simply the computer model. So let's try to load the data sets. And then these are a couple of useful libraries. Like we import the time, and this time is just going to, we use it to time our algorithm, how long it takes to run. Then NumPy is like the gold standard for matrix modification and manipulation. Pandas is for handling data frames. Seaborn and Matplotlib are both for visualizations. And then we have the Minimax Scalar and others, which we are going to talk about as we proceed. So whenever you do machine learning, the Y variable is always called the outcome, which is what you want to predict. In classical statistics, we call it dependent variable. And those things we want to use in predicting are called the features. So in classical statistics, we call them independent variables. So now we know what to do. We want to try to learn the rules, which is simply machine learning. However, to do that, we need some more tools. And that is where we introduce the concept of training and testing sets. So for the algorithm to learn, like we said, we expose it to some answers and to some inputs. So for the algorithm to learn, we have to expose it to some examples. These examples are in what we call the training sets. So whenever you see, we say we divide our data into training and testing sets. So the aim is to use the training sets to actually teach our model how to learn F. And then the testing set is what we use in evaluating our model. So we train and then we evaluate on the testing sets. So that is what we do in practice. There is no rule for the division, but we know that a higher percentage has to go to training and then a lesser percentage goes to testing because we want to expose our model to a lot of examples. So we are going to divide our data into 80% training and 20% testing. And this is done here. And then we set this random state to 0, which simply makes our result reproducible. So whenever you do the training and testing, everything you do has to be on the training. And then the only thing you do with the testing is to evaluate your model. The reason for this is you're trying to mirror the reality because in reality, you don't know the kind of data coming in, so you don't touch the testing sets. You only use it, you only evaluate your model using the testing set. However, before building your model, we would usually visualize our data but note that this is only going to be done on the training set. So there is a couple of visualization techniques that are available out there. So, but for today, we are going to use the scatter plots matrix. And then what this actually does is to give us a pair, a matrix, a symmetric matrix, where each panel of the scatter plot matrix is a scatter plot for a pair of features or variables whose identities are given by the corresponding row and column labels. So for example, right here where my cursor is, this is incidence angle and this is snow depth. So this is a scatter plot that gives us the relationship that plots the relationship between incidence angle and snow depth. And then for the main diagonal, the main diagonal actually gives us a variable and itself. And if we simply plot a scatter plot of a variable and itself, it's just going to be a straight line. So it really doesn't give us much information. So what pandas is going to do is to give us like a shape of the distribution of the data set on the main diagonal. So that is what is happening here. Then after that, there's a lot of plots depending on what you are doing. But for now, we are just going to stick to this. And then other things we do is the descriptive statistics. And then descriptive statistics are just techniques that describes your training set. And then pandas has a method called describe to do that. So pandas gives us what we call the 5-number summary, and then it gives us the mean and the count. So the 5-number summary was a concept by Tukey in a very long time ago. And the idea is if you want to understand the data, there are 5 things that you look at, and he called them the minimum, the 25th percentile, the 50th percentile, the 75th percentile, the maximum. So what the mean is just the mean is simply the arithmetic mean. The standard deviation gives us how spread out the data is. Then the minimum gives us the minimum value. The maximum gives us the maximum value. The 25th percentile gives us a value for which 25% of the data is below that value and 75% of the data is above that value. Then for the median, it's the 50th percentile, which tells us that 50% of the values in a particular variable is below that number, and then 50% is above that number. Then same thing for 75th percentile. It says 75% of the values in a variable is below that number and 25% is above that number. So using amplitude as an example, the arithmetic mean of amplitude in this data set is 0.15, and the standard deviation is 0.04. So if the standard deviation is 0, it means the variable is just a constant. That is, it doesn't vary at all. So the higher the standard deviation, the more varied the variable. Then the minimum amplitude for this data is 0.07. The 25th percentile is 0.12 approximately. The median is 0.15, which means 50% of the amplitude values in this data is less than 0.15 and 50% is greater than 0.15. So we've looked at our data and there are lots of techniques to do that depending on what you want to do. So the next thing I want to move in now is feature engineering. And this is where we spend most of our time when we do machine learning. So to different data scientists, feature engineering means different things. So for example, someone who works with a text, feature engineering means how you can transform your text into variables. But for us, in this tutorial, we will define feature engineering as the art of manipulating and transforming data into a format that optimally represents the underlying problem. So everything you do between getting the data and fitting your model, you could call them feature engineering. You transform your feature such that it is acceptable to the model that you want to use. And then feature engineering, we have different types of them. So we're just going to talk about them. We won't dwell too much on that. So we have feature improvements. So what you might want to do during your feature engineering is to improve your feature. And then some examples of feature improvement include the normalization, the missing value imputation, and the likes. You could want to construct a new feature. So in that case, you could combine some features to get a new one, or you get some new feature. Another one is feature selection. So at times you have too many variables and you want to drop some of them. So when you're trying to drop the features, this is also called feature engineering. And then there are various techniques for doing that, like the hypothesis testing, the information gained from tree-based models, etc. We could also have feature extractions, such as the principal component analysis, singular value decomposition, etc., etc. So for this data set, so it is worth noting that this data set has been cleaned. There is a separate notebook for that for anyone who is interested. But for this tutorial, we are just going to talk about the feature improvements, and the only one we're talking about is normalization. So the features are actually measured on different scales. For example, the scale of amplitude is not the same as the scale of phase. So when you do machine learning, variables with higher magnitude tend to dominate the training, and then you think they are the most important when you are trying to get the feature importance. So for that reason, we try to put all the variables on the same scale. And there are a couple of methods to do that, but two common ones are normalization, and then we have the standardization. So standardization is common among statisticians, and then we use it because it doesn't suffer when our data contains outliers. However, if the data does not contain outliers, then you could project all the variables into a unit interval 0, 1, such that the minimum for all variable is 0 and the maximum for all variable is 1. This process is called normalization. So it is worth noting that whether the predicted variable should be normalized or not, it's an issue of preference. So I might decide to normalize mine, I might decide not to normalize mine. However, if you normalize your outcome variable, when you predict, you are predicting a normalized value, so you should get the inverse transform, that it transforms the predicted value into the original scale. So to do that, we have what we call the Minimax Scalar, which does the normalization for us, which is where the minimum value is 0 and the maximum value is 1. Note, everything you do has to be on your training sets because you don't know what data is coming in. So the way you scale or the way you normalize your test set is to use the parameters that you learned from the training set in transforming the testing set. So this is important. For the training set, you use the fit transform. What it does, it fits and then it transforms. So it has some parameters like the mean, the maximum, and the minimum. And then when you want to do that on your testing set, you only transform, which takes the parameters learned from the training set to transform the testing set. So let's proceed. We would normally want to separate our x from the y, which means we normally want to separate our features from the outcome. So why do we even have to estimate f? Because we said in machine learning, what we do is to estimate that function that maps the inputs to the output. So why do we have to do that? We have to do that for two reasons. The first one is prediction. So in this case, the features are available, but there is no explicit rule for obtaining the outcome. The other one is inference. So in practice, we don't always need prediction only. At times, we want to see the effect of the inputs on the outputs. So in that case, what we are doing is called inference. So how do we estimate F? That takes us to the machine learning algorithms. So depending on who you ask, machine learning algorithm is divided into different sets. So it could be divided based on the amount of supervision needed. It could be divided based on how the data comes in. It could be divided based on how the model is trained. Maybe it is instance or model based. But for this tutorial, we will be dividing our machine learning algorithms based on the amount of supervision needed when you're training your model. So based on that, we've got 4 categories. We have the supervised learning, we've got the unsupervised learning, we've got the semi-supervised learning, and then we've got the reinforcement learning. So for today, we just concentrate on supervised and unsupervised. So for the supervised learning, the idea is straightforward. you have something to predict. So in that case, you are looking for a function that maps your input to the output explicitly. So in machine learning terms, you say you have an outcome that supervises your input variable. That is, it tells your input variable whether the prediction is correct or not. And then you have the unsupervised learning. So in that case, you're not predicting something. Rather, you're trying to look at the relationship between your features or how you can group your observations based on how similar they are. So for today, our task is supervised learning because we have an outcome to predict. Also, we should note that the outcome you want to predict can either be a number, which is a numeric value, which is something measured on a numerical scale, or it could be just some categories, just like you might want to predict whether someone has a cancer or not. So in machine learning terms, we call that classification. And then when you want to predict something that is numeric, we call that regression. So for today, we are predicting snow depth, and that is a regression problem. So for now, or to the end of this tutorial, all our concentration is going to be on the regression problem. So now that we know the reason why we estimate F and how to do that, so let's talk about our machine learning installation guide. So for this tutorial, every package that we will be using comes pre-installed if you get your Python through the Anaconda distribution. The only thing that doesn't come with it is the Tensorflow. And Tensorflow is an open source platform for machine learning, which was developed at Google. And then there is a link that takes you to the website where you can read more about it. Keras, on the other hand, is an API that connects, that uses TensorFlow at the back end. And then it is easier to use. You can easily build your deep learning models on those. And then to install your TensorFlow, you can simply do pip install TensorFlow, and that's going to work for you. So now we'll assume everyone has TensorFlow and Keras, and then we'll continue with the other part of the tutorial. So most machine learning techniques can be characterized as parametric or non-parametric. So now I'm talking about supervised learning because that is our concentration for this tutorial. So parametric is quite different from what a statistician will call parametric. So in this case, when your problem is reduced to estimating parameters, you call it a parametric technique. So the parametric technique is going to simplify the problem of estimating your F, which is the machine learning algorithm, to parameter estimation problem. So, but it has a disadvantage because before you can estimate the parameter, you have to assume a shape. So the problem is, in most cases, the shape doesn't match the reality, and then it tends to have lots of error. So a good example of that is the linear regression, which is a parametric approach in which you assume that the relationship between your input and your output is a linear one, and then you just reduce the problem to estimating the betas, which are the coefficients. Then on the other hand is a non-parametric, which it doesn't assume any shape for F, but what we do is try to estimate F that gets as close to the data points as possible. The disadvantage of non-parametric is that it requires extensive training observations to estimate F accurately. And then common examples include the random forest, support vector machines, neural network. So what to use depends on what you want to achieve. So if your goal is inference, then you probably want to use the parametric approach because it's easy to know how your X affects your Y if you use a linear regression. However, it is hard to know how X affects Y if you use the likes of support vector machine / neural network. So the previous year, last year, we did one parametric, one non-parametric. Linear regression was the parametric we did last year, but this year we will be doing the random forest, which is a common technique that we use a lot in geosciences. And then I think one of the reasons why we use it a lot is because it gives us what we call the feature importance. So let's talk a little bit about random forest. So the building block of random forest is decision trees. So decision trees, when you use it for classification, you call it classification tree. When you use it for regression, you call it regression trees. So because we want to solve a regression problem, so we'll stick to the regression tree word. So the concept of regression tree is very simple. You keep asking questions, and then your answer tells you what to ask next until you get to a stopping criteria. So in machine learning terms, you said we call it a technique that splits the feature space. So when we say feature space now, it means all possible values for the feature. This is called the feature space. So it split it into two, then further splits the subregions into two until a stopping criterion is reached. And then the predicted value for an observation is going to simply be the arithmetic mean of the region where it falls. So now let's talk about performance evaluation. So after this, we'll see regression tree in action. So how do we know if our model is doing well? I mean, we don't just want to fit a machine learning model, but we want it to do the job. So each time we try to estimate the true value using a machine learning algorithm, discrepancy um, between the observed and the predicted has to be quantified. So depending on what you are doing, the method you use to quantify is different. However, the notion of loss function has to come in, which is a function that quantifies the error you sustain from predicting your outcome using a machine learning algorithm. So it's a bivariate function that takes the predicted and then the true value. And then in simple language, what it does is how well is our machine learning doing for a particular point. There are a lot of them in practice, but the two common ones for regression problem are the squared error loss, which simply subtracts your y and the predicted value, and then it squares it. So the square is coming in is for mathematical convenience because at times you could have a positive and negative error, and then they tend to cancel out each other. Then you think your machine learning is doing well. However, with that square, it makes us reach the minimum of our loss function. Then another thing you could do is to subtract and take the absolute value. So this is called the L1 error, L1 loss function. So what I just said now, if you notice, is just for a single point. However, what you are interested in is to get to quantify our error over all the points in our data set, and this is called the empirical risk. So in machine learning, the empirical risk is what we want to minimize. So the empirical risk that is corresponding to the squared error loss is called the mean squared error. And then in machine learning, all we do is to try to minimize the empirical risk. So now let's talk a little bit about the setup for random forest. So we'll bring in the pipeline, we'll bring in the random forest regressor, we'll bring in the decision tree regressor, and then we'll bring in the train test plate. So let's build a simple regression tree. And then for now, don't worry about what this max depth is, but we are setting it to 2, but random state is just to have a reproducible result. So, and then let's plot our regression tree. So to plot our regression tree, we use a function that is provided by scikit-learn. And then this field here just tells us that I want some color in each of these nodes. The font size is how big you want those fonts to be. The node IDs are these labels for each node, like node 0, node 4, node 1. And the rounded simply allows the edges of these boxes to be curved. Then the proportion gives us the percentage number of observation in a particular node. And then the feature names is going to give us the feature. So let's try to explain the tree that we have above. This first node here is actually called the root node. And then in this case, you would see that we have the INC angle less than or equal to a particular value. So for now, let's keep how that value was gotten, but let's explain what is here. So what the root node does is it simply assigns the incidence angle that are lesser than or equal to 0.818 to the right node, and then the ones that are greater to the left node. So we say it does some kind of binary splitting. So it's going to ask a question: is your incidence angle less than 0.818? If true, it comes here, and if false, it goes to the other place. So, and then in this case, we set our max depth to 2 the last time. It means I just want what? 2 depth, like this is the first one, and this is the second one. So this is where the max depth is. So in total, we've got 4 regions, which is node 2 here, node 3, node 5, and node 6. So overall, the regression tree is going to split the observations into 4 disjoint group or regions of feature space. The first region is where the incidence angle is less than or equal to 0.818, and the phase is lesser than or equal to negative 8.432. So this is what I'm saying. So the first one comes here and then goes here. So the second region comes this way and goes this way. The third region comes this way and goes this way. The fourth region comes this way and go this way. So that is how we have the 4 regions. So the predicted value for any observation is simply this value here. So any observations that ends up in this region is going to be predicted as 0.712. So that is how that is done. So in regression tree terms, the node 0 is called the root node. Then the internal nodes are the node 1 and node 4, which is this one here and this one here. And these 4 nodes are called the terminal nodes or the leaves in our model. And then those are the nodes that holds the predicted value. So we've mentioned that there is a recursive splitting, that it keeps splitting into 2, but how do we construct these regions? Like how do we split these regions? So our goal is to find regions such that the expected loss is minimized. So to perform the binary splitting, we consider all features in the feature space and all possible cut points. So we look at all possible cut. So for example, we take incidence angle, look at all possible cut points, and then we pick the cut point that leads to the greatest reduction in the expected loss. So here we are using the mean squared error. So this was selected because it led to the greatest reduction in the mean squared error. So there's a question of, do we have to go through all possible values? There are different algorithms. Some say you have to go through, but there are different algorithms in the literature for that. So that is how those things are done. And then the stopping criterion is could be the maximum depth. So because if you don't stop your tree, it's going to keep going, keep going, keep going, and then you have a very big tree. So you could stop the splitting by specifying the maximum depth or specifying that the minimum samples for it to split. So in some cases, you tell it that, okay, when I have 2 or 5 samples in a particular node, don't split it. So in scikit-learn, that is controlled by the minimum sample split. So that's a little bit of what regression tree is. To make predictions now, all we have to do is to ask some questions. So as an example here, we selected one of the elements of our test sets. The amplitude is 0.198, the coherence is 0.866, the phase is negative 8.84, and the incidence angle is 0.79. So now let's try to make this prediction. So if you notice, our tree uses only 2 variables, which is the incidence angle and then the phase. So it implies that for now, what you're just interested in is the phase and the incidence angle. So the phase in this problem is 0.797. Then we ask, is 0.797 less than or equal to 0.818? The answer is yes. So it goes to node 1. And then in node 1, the variable you have there is face. So then you ask, is your face, the face value here is negative 0.844. Is that value less than or equal to negative 8.423? The answer is yes. So it comes to node 2, and then our prediction is 0.711, which is the value in this node here. So that is how it predicts. So you could predict yourself by just asking series of questions until you get to the terminal node. So before proceeding, does anyone have any questions so far? All right. So now, what is next is a notion of feature importance. So in some way, some researchers with big brain have been able to come up with a way of measuring the importance of features when you use decision tree. So the algorithm is the total amount by which the empirical risk, so in this case, the mean squared error, is decreased due to splits over a given predictor is documented. So the larger this value is, the more important the variable is. In scikit-learn, the implementation of this normalizes the variable importance so that it adds up to 1. So in scikit-learn, what you see is the importance adds up to 1, which is simply the normalized version of the variable importance. But we will try to do this manually and try to compare it with what scikit-learn does. So this is the formula here. And then what it simply does is, for a variable, it goes to all node where it splits. And then this W here is actually the proportion of the observations in that particular node. And then this C here is actually the mean squared error at that node. And then it does it subtracts that of the left and the right node from the parent node. So for example, for incidence angle now, incidence angle is in node 0 and it's in node 4. So now let's try to calculate this first part. So for node 0, this is 0.396, which was gotten from here, which is the squared error at that particular node. Then you multiply it. So, okay, so for this place now, you have 100% of the observations here. So you're simply multiplying by 1. Then you look at the 2 child nodes. So the one that goes to the left, so the squared error there is 0.156, and then the sample is 79.9%, which is simply 0.799, so which is what you have here. And then on the right node, you've got the squared error to be 0.07, and then the samples there is 20.1, which is 0.201, which is what you have here. Then you compute this value, and you do it again for node 4. And the reason we are doing for node 4 is because we also have incidence angle in node 4. So if you do that, and you add them together, that is going to give you the importance of incidence angle, and that is calculated to be 0.26. So we do the same approach for the face, and then we calculated that to 0.042. So in scikit-learn, there is a way to get the unnormalized version. So we try to do the normalized and the unnormalized version from scikit-learn, and then we compared with our values. So you see that the values are the same. So that is how scikit-learn actually computes the variable importance. So now we do this, and so when you plot, you see that this is going to add up to 100% because scikit-learn actually normalizes these values. So here, because 80% is for incidence angle and just about 20% is for phase, so we conclude that incidence angle is more important. So in reality, it meant that splitting on incidence angle led to greater reduction in the mean squared error. So now that we have, so there's a simple exercise here, which is compute the normalized importance manually and compare with scalar. So what I did was the unnormalized, so you could normalize it, which is just taking it to percentage. So random forest. We've talked about the building block. So now let's talk about the technique itself. So we would have heard that random forest just combines multiple regression trees, but it has to combine it in a specific way. So I just brought a phrase or a proverb. It's an African proverb that said, if you want to go fast, go alone. If you want to go far, go together. So I try to link it to random forest. Individual trees are faster to train, and then multiple trees are a little bit slow, but they do better. So something like that. So if we, based on what we've learned so far, if I duplicate those trees, it's simply going to give me the same value because each tree are going to predict the same thing. So which means I have to bring in some randomness. And this is what brings the first notion. So random forest is an ensemble machine learning method. An ensemble simply means you combine weak learners or weak models, and then you build a stronger one from the weak ones. So, and then in random forest, this is done using bagging, because I mentioned that if you just duplicate the same tree, they're just going to give you the same prediction. And if you average it out, they give you the same value. So for random forest uses the concept of bagging. So bagging is a combination of two separate words. We have the bootstrap part and we have the aggregation part. So bootstrap is a popular resampling technique where you resample your training set with replacements. So, which means you create multiple training sets from a single training set by sampling with replacements. So the individual sample you created is going to be called a bag. And then the aggregation part is, now that you've introduced some kind of randomness, it means each tree are going to predict different things, and then you bring together their predictions, you average it out. So this is called bagging. So mathematically, it means if you resample 1,000 different training sets from your training observations, you're going to call that B. So for each of those B, you are going to train a regression tree, and then you average out their prediction. This is bagging. So in random forest algorithm, regression trees are built on the different bootstrap samples, and then the result is a forest of regression trees. So that's where the forest came from. So forest of regression trees. So now the question is, what makes the forest random? So if you only resample, so what you did is just called bagged regression trees. So it's not random yet. You have a forest of regression trees, but the forest is not random. So what makes the forest random is at each split, you don't consider all the variables you have in your model. You only consider a randomly selected sample. So when you combine bagging with random feature selection at each internal node, then you just built a random forest. So that's the idea of random forest. So now we'll build a random forest and we'll see how it works. So for now, we are going to set our max depth to 2, and we set our number of estimators to 2. So when I say number of estimators is 2, it means I'm just resampling twice. And then for each of these 3, I want just 2 depths, like the maximum depth should be set to 2. And then the random state is 0. In this case, I want a reproducible result. So now we have this tree, if we plot them side by side. So these are the 2 trees in my forest. And then the idea is the same as before. The way you do the prediction and everything is the same as before for the individual trees. So in this case, when you want to make prediction, what you do is you make a separate prediction from the tree on the left and make another prediction from the tree on the right, and then you average them out. And then this is just what we have here. So if we follow the same approach we used earlier for the tree on the left and the tree on the right, because you have 2 trees in the forest, you add up the predictions and divide it by 2, then you get the prediction of the random forest. And that is what random forest simply does. So it combines many weak learners, many weak decision trees, and it builds a stronger one. I would call that a random forest. So it is what notezy, or it's very important to note that the implementation of random forest in sklearn or scikit-learn is a bagged regression tree. And then so if you come here, so this is the documentation, and then the maximum feature defaults to 1. So which means it uses all the variables for splitting. And that is simply what a bagged regression tree. And that is what is noted here. The default of 1.0 is equivalent to bagged trees. And more randomness can be achieved by setting smaller values each zero. So if you have a lot of features, we set that to maybe 0.3, you could take the square root, you could take the log 2, or just put values there. So just SWOT noting. All right, so now feature importance. So we just do the same thing. So we get the feature importance from the left tree, get the feature importance from the right tree, and then you average it out, and then you get the overall feature importance. And then what random forest does is it normalizes it so that they add up to 1, using the same approach as before. So I've got a simple exercise here also. So compute the random forest normalized importance manually and compare it with the sklearn output above. So putting it all together, random forest, now we know the basic concept of random forest. So in reality, we won't want to do those things separately. So we use the concept of pipeline. So sklearn has a very rich method called the pipeline. And what it does is sequentially apply a list of transformers and a final estimator. So it makes coding very easy. And you don't have to think of trying to use the values you learned from your training set to normalize the test set, and it does those things for you automatically. So the pipeline is going to take the steps. So in this case, we just have 2 steps, which is the first one is to get the normalized version of each input variable, and then it passes the normalized version to the random forest regressor, and then it fits it down here. So that's it. But you could do many other things like input missing variables and the likes. A lot of transformers can go in there. So that's that about random forest for now. Then the second one I'll be talking about is the neural network. And then neural network is probably one of the most popular aspect of machine learning today. And then the building block of deep learning itself are neural networks. So neural networks are machine learning techniques that was inspired by the functionality of the biological neurons. So they don't model the brain, but the concept was inspired by looking at how the brain functions, something like that. So every neural network consists of 3 layers. We've got the input layer, we've got the hidden layer, and then we've got the output layer. So now, when you hear deep learning, it simply means you have more than 1 hidden layer. And then the word originally came from trying to look at the depth of the hidden layer. So that's where the deep comes in, like the depth of the hidden layer. So now, to understand the functionality, let's look into what a single neuron looks like. So for a neural network, this is how we normally represent it. So we've got the input layer, we've got the hidden layer, and then we've got the output layer. So each layer in a neural network consists of small circles or small units, usually represented with a circle, and this unit is called a neuron. And what a neuron simply does is it takes input from other neurons, do some mathematics, and passes the output to some other neurons. So each neuron in the input layer here represents a feature. So in our case, we've got 4 features. So our input layer is going to have 4 nodes. And then each of these neurons is connected to some neurons in the input layer. And then each interneuron connection has a weight. So for this Z1 here, it takes an input from all of these X's, and this Z2 also takes input from all of these X's. And then these lines, they have a weight. So each of these interneuron connection has an associated weight. And then for each of the node, you have some kind of bias in there. So the configuration of the hidden layer controls the complexity of a neural network. So if you have a hidden layer where it has a lot of nodes in the hidden layer, then it's going to take longer time to train. So this is what controls the complexity of a neural network. And then a neural network that has more than one hidden layer is called a deep neural network, while that with a single layer is called a shallow neural network. And then the final layer is called the output layer, and it holds the predicted value of observations that are passed into the input layer. So every interneuron connection has associated weights, and the weights are what the neural network learns during training. So when you say you train a neural network, you're trying to learn the optimal weights such that when you pass an input, it gives you a prediction that is closest to the true value. So this is the simplest kind of neural network you can have. And then if there are other families of neural networks, but for now, we'll call this one the feed forward because the information keeps going forward and it never comes back. There is no loop. So this is called a feed forward neural network. And this is what a neuron looks like if you bring it out. So it has some weights, it has a bias, and then the output is actually taken to another node. However, it is worth noting that what I just described now can be thought of as something like this, which is simply a linear regression. So at times you may consider neural networks like some beast of linear regression. Each node has some linear regression. So where nonlinearity comes in, because linear regression simply assumes a linear relationship. So where nonlinearity comes in is called the activation function. So for each of these values, you apply some kind of function that we call activation function. And this activation function introduces nonlinearity into our model. So there exists a number of activation function in practice. You can always go to keras.io, where you have a lot of them there. But the three common ones are the sigmoid, the hyperbolic tangent, and then the rectified linear unit. And so far, rectified linear unit is the most used, and it's called, for short, we call it ReLU. So what sigmoid does is it squashes your value between 0 and 1. So whatever value you get after your linear regression inside the node, it squashes it between 0 and 1. For the hyperbolic tangent, it squashes it between -1 and +1. And then for the rectified linear unit, it just picks the maximum between 0 and that particular number. So this is what the shape of those things look like. So any number you pass into the sigmoid, it squashes it between 0 and 1. For the hyperbolic tangent, it squashes it between 1 and -1. And then for the rectified linear unit, it just gives you the maximum of 0 and that number. So I mentioned earlier that there are families of neural networks. So feed-forward neural network, which is the one we'll be using today, is the simplest of all, and we would normally use it for structured data. So structured data are data that comes on a table format. Then we have the convolutional neural networks, which is the gold standard for computer vision. When you want to do image segmentation, anything with image, we would normally use convolutional neural networks. We have the transfer learning, which prevents us from starting our training from scratch. So if we have like a neural network that recognizes the eye, and what you want to do is to recognize the whole face, and you could start by using the neural networks that can recognize your eye before proceeding to the whole face. This is called transfer learning. We have the recurrent neural networks, and then this is well suited for time series. They use it for drawing generation. We use it for text because they are sequence of stuffs. We have the Encoder Decoder, which is commonly used for machine translation. So you give it a particular language, it outputs another language. So the neural network that we normally use for that is Encoder Decoder. We have the GANs, which is the generative adversarial networks. They are usually used for 3D modeling, like for video modeling, for animation, etc., etc. And then we have the graphical or the graph neural networks, which are normally used for graph data, like the ones gotten from the likes of Facebook. You want to see how people are connected. So normally use the graphical neural network for that. So for this tutorial, all we need is the TensorFlow, and then from TensorFlow 1 or TensorFlow 2, I think, it now comes with Keras. So previously you have to install Keras on its own, but Keras is now a part of the standard TensorFlow library. So all you have to do is just install the TensorFlow alone. So the way neural network works, the mathematics is at the appendix, but for each of these, we go forward and get a prediction, and then we compare our prediction to the true value. So if it is close enough, we might specify a threshold. You stop your training. Otherwise, you are going to adjust the weight. So this weight adjustment is done through what we call the gradient descent. And then you can find more about the gradient descent in the appendix. But for the gradient descent, there is one important step that does the differentiation. So this is done using the back propagation. But the details of those things are a little bit above the scope of this tutorial. So to do that, to do your neural network in Keras, there are different APIs that Keras uses for building neural networks. We've got the Sequential API, which is the simplest of all, and which is just a list that contains the sequence of the layers. Then we have the Functional API, which is a little bit advanced, but for now we are going to use the Sequential API. So you start by specifying the Sequential API. Then I would always seed it to have reproducible results. So this number can be any integer. I just choose 1,000, can choose it to anything. So there are different layers. We have the dense layer, which is what I just explained here, that every neuron in the hidden layer is connected to every neuron from the input layer. So that kind of layer is called the dense. And then I specify the number of units here, which is, I'm specifying 1,000 here, but there is no explicit rule for that. We don't know the best value, you just have to keep trying different options. However, some researchers have shown that the more the nodes, the better the performance. So, and then I stacked it with another input layer, another hidden layer. Then I added another one to it just to show you, just to show that you can have as many as much input layer you want, hidden layer as you want. And then the activation here, I'm using ReLU sigmoid. You can use anything you like. So the last layer is the output layer. And then the number of nodes is 1 because we are predicting a single value. I should note here that we don't activate a regression problem because I showed what the activation does. It squashes the number between some interval. So, but in that case, at the output layer, we don't need any form of squashing. So we just output the true value. And then after you do that, you want to compile. And then when you do the gradient descent, as the name implies, it's like you are descending a hill. And then we have what we call the learning rate, which controls how fast you want to go down the hill. So it might be tempting to go faster, but it's not always optimal because you might jump the minimum value because the curve is not a smooth one. So that's some mathematical problem. We say it's not a convex problem, but what it means is the curve is not smooth, so you can't just keep coming. So if you have a larger learning rate, you might jump over the minimum. And if you have a smaller learning rate, you might not get to the minimum. So you have to try different values to see the one that works. So, and then we have the loss, which you already know what it is from above. So we're using the mean squared error. Then we have the optimizer, which is just some form of function that makes our training faster. So we've got quite a number of them. We have Adam, we have RMS prop, we have ADA delta, we have ADA grad. We don't know the best. You just have to try them. But as far as what I've seen, ADAM tends to work better, and then also RMS prop. But really, we don't know the best, so you just have to try. So after fitting this model, you can actually draw out, you can draw out the architecture of your model. So it tells you you've got dense layer all through, and then the number of neurons in the first one is 1,000, so as we have specified here. However, it tells you the parameter is 5,000. So the idea is this. So if you have 1,000 of these neurons here, and then for each 1,000, you have four you have four connections from the input layer. So you simply have 1,000 multiplied by 4, which is 4,000. And then I mentioned that for all of these units, you've got the bias term. So if you have 1,000 biases for the 1,000 node, so that gives you 5,000, which is 4,000 plus 1,000. That is how Keras calculates it. And then the same thing applies to other ones. And the calculations are here for verification. So after compiling our model, we would want to fit the model. So that is the sequence for which you use in Keras to specify the architecture, you compile, and then you fit. So here we find the neural network weights using the data in the training set. Like I said earlier, when you fit a neural network, you're just trying to find the optimal weights. So an epoch is when an entire batch of the training set has been used. So like I said earlier, that you pass in the training set from the input layer, and then you have a prediction there. So the number of times for which you want to do this passing, or the number of times for which you want to adjust this weight, you can control that with the epoch. So if I set my epoch to 5, so that means my data goes in 5 times, and that's all. So there is a problem here also, because if we have a very large training set, the training can be painfully slow, which means it has to go through all the elements in your data set. So there are some approaches that says, no, instead of going all through, just randomly pick one and go through it. And that is called the stochastic gradient descent. But the one we would normally use is the batch. So we normally specify the batch size to anything we want. So in most cases, you specify the batch to 32, 64. That's how people do it. And then when it trains, it only goes through 32 randomly selected if you specify 32 as a batch size. So then we have the validation split. Yes, neural network can get so complex, and then we want to see how it performs so that we can know when to stop training. And with that, we always use a validation split. What the validation split does is whenever you fit your neural network, it is going to try to predict, and you see, so it's going to try to predict using a held out test set. So for now, we call that test set the validation set, which just shows whether my neural network is overfitting or underfitting. So in simple language, what overfitting is the neural network is going to perform well on the training set, but when you apply it on a held out test set, it's going to perform very, very poorly. So with that, this is what you are trying to see. That is why we have this validation split. So if there is a large difference between your training loss and the validation loss, you know your neural network is probably overfitting, and then you have to do some adjustments. That is what this is actually, that's what you do that validation splits for. So now we fitted our neural network, and then we want to compare our results. So there are different ways to compare results in practice, depending on the problem you're solving. So because it's a regression problem, I'm just talking about 4 here, but we have a lot of them. Talking about the root mean squared error, the mean absolute error, the mean absolute percentage error, and the R square, which is coefficient of determination. So the root mean squared is simply the square root of the mean squared error from the test sets. So which means you use your optimal model to predict the elements of your testing set. You compare the prediction with the actual value. And then for each of those comparisons, you square it, then you get the mean in the end. That is, after getting the mean, you get the square root. So the idea is the square root takes that back to the unit of your y variable. So it makes it comparable. And then the MAE is the mean absolute error. The MAP in some way puts the error on percentage, so you can know in terms of percentage what's the error. And then the R square is a value between 0 and 1. So the closer to 1, the better it is. So if your prediction is perfect, you have R square of 100%. So we write a performance, we write a function that does the performance and outputs it. So for now, if you compare the performance, you see that random forest is doing better compared to neural network. We've not done any optimization so far. So this is just first comparison. And then at times, random forest is so effective that it performs better than the neural networks. So in some cases, you want to visualize your error, and then this is how it looks like. So you see that for the random forest, the values are closely packed compared to the deep neural networks. So if the values, if the predicted value and the true value are the same, then you're simply going to have a straight line. So the further away, the spread out from straight line, the closer to straight line, the better the model. So random forest is closer to straight line compared to deep neural networks. So we'll say random forest is still better for now. And then at times you want to look at the distribution of your error. This is not useful in all cases, but in some cases where inference is the goal, we want to look at how our error looks like, because as some model actually make explicit assumption about the distribution of the error term. So in that case, you want to look at the shape of your error. For example, the linear regression, it assumes that the error follows a normal distribution. So, and you want to look at that visually. Now, this is the first thing, or this is the basic thing we do in machine learning. But there are main challenges in machine learning. It's not just that easy. So the first one is it could have a bad data, and bad data could mean different things to different people. So, but some of the examples or some of the things you can link bad data to is our insufficient training data. So some researchers have shown that for the non-parametric approach, you need more data, you need more examples in your training set. So if you have insufficient training sets, then your model is probably going to not be well trained. Then non-representative training data, this is very, very important. What this means is if the kind of data that you use in when you launch your model into production, if it's different from the kind of data for which you have trained it, then your model is going to perform poorly in production. And then it could be irrelevant features, and then you could do some kind of feature selection. The other one is bad algorithm. Bad algorithm could mean different things to different people also. It could mean overfitting the training set. And what that simply means is your model is going to perform well on the training set, probably 100%, and on the testing set, it performs very, very poorly. So that is called overfitting. Underfitting, in simple language, means your model performs poorly both on the training and the testing set. So which is the lesser evil? I think bad algorithm is the lesser evil. So this is my opinion. A good data is better than a good model, in my own opinion. So how do you improve your model? There are different ways to do the model improvement. And then you could have regularization. And regularization also means different things to different people. So to some model, like neural network, regularization could mean early stopping. For models like linear regression, regularization could mean you have to penalize your loss function. So, but some common ways to regularize is early stopping and dropout. And then another way to do it is hyperparameter optimization. So we don't always have the best hyperparameter value. So we don't know the best value. So we have to kind of do some kind of tuning to get the best value out of it. So hyperparameter optimization. So what hyperparameter optimization is, in simple language, is There are some parameters that are not learned when you train your model. So you have to specify them before you train your model. This is called, or this kind of parameters are called hyperparameters. For example, in your decision tree, you have to specify, or in your random forest, you have to specify the number of estimators you want. So that is not learned, that has to be specified. So that is called an hyperparameter. But in reality, you don't always know the optimal value of that, so you try different values. So the process of trying different values is what we call the hyperparameter optimization. And this can be done in two ways. We have the validation set approach, and I have the cross-validation. So what the validation set approach simply means is, and this is commonly used when you have a very large training set. So you kind of, from your training set, you also divide it into training and testing again. But in that case, you won't call that testing, you call that validation. So the idea is you try multiple values, multiple values of the hyperparameters on the training set. Then you test the performance on the held out test set, and you see how well it does. So in the end, the hyperparameter that leads to the greatest performance is what we use for training the entire training set. And then we have, on the other hand, we have the cross-validation, which is used when we don't have a very large training set. But the idea is you divide your training set into chunks. So if you say 5-fold, that means you divide your training set into 5 different chunks. So each of the chunks is going to serve as a test set repeatedly until all the chunks have served as a testing set. So this is the idea here, illustrated by this. So here, this is a 3-fold cross-validation. You divide your training set into 3 folds. Then the training is going to be done on chunk 2 and 3. You validate that on chunk 1. You keep the performance. You do that so that all the chunks have served as testing set, and then you average out your performance. So the combination of hyperparameters that leads to the best performance is going to be selected. So in scikit-learn, we do that using what we call the grid search CV. So the grid search means you actually have to specify some grids of parameters, and you search that grid to get the optimal one. And then the cross-validation is the other part of it. So this is how it works using the grid search CV. So up here are possible parameters to tune. So if you do get params, it's going to give you the possible parameters you can tune. And this is just we trying to tune the minimum sample split as 2 and 3, the number of estimators as 50 and 100, and then the regression max steps as 3 and 5. And then we look at how it performs. And then for the neural network also, we can, there's a wrapper in scikit-learn that can help us do that. So we just create like a function and do the same thing using a pipeline. And then here, what we did here was to optimize the Adam and the RMS prop optimizer, the number of nodes in the hidden layer, and the number of nodes in the second hidden layer. However, Keras has an inbuilt function for doing that tuning. It's called Keras Tuner, and it's a more advanced one. But I just thought, because I used the grid size CV for the first model, I should just do it on the second model. But I could use that on the, could use the Keras Tuner, and it gives you more options than this. So that's that about that. And then we get to the final part of the tutorial, which is how to deploy a machine learning model. So now we have a model that lives on our Jupyter notebook. So how do others get to benefit from this model? So this is called deployment. So, and then deployment also means different things to different people. So, but for this case, in this tutorial, would consider deployment as how do we make the model available for others to use. So there are quite a number of steps for that. So to launch our model into production, there are steps. The first one is you save the model. That's the first thing. The idea is if I don't save this model, once I'm off this Jupyter Hub, my model is gone. So if my model was hard to train or it takes many time, I have to do the same thing every time I open my model. So the first thing is we save the model. And there are different ways to save model, but I consider Pickle as a great option because Pickle is used by almost everyone in Python to save complex objects. So what it does is it saves the model and then so talking about deployment of models. So our model lives on our Jupyter notebook. Others. This is called model deployment. There are quite a number of steps to do that. The first one is to save your model. So some packages like TensorFlow has an inbuilt way of saving the model. But in general, if you use some other kind of packages outside of TensorFlow, you could pickle it. Now what pickle simply does, it helps you save the binary version of some complicated object in Python. So you save it like a binary, you save the binary format and then you're able to load it again. So when you load it, everything is in there and intact, and then you can apply it. So with that, you don't have to retrain your model every time. So after saving the model, the next natural thing is to serve the model. So what does serving model mean? It means the process of making the model available to others. And this is usually done using web services. A simple way to implement web service in Python is Flask. So Python has a package called Flask, and it is used to serve models for web applications, web development. So you could serve a model on Flask. So now the next thing after serving the model is a deployment. So when you serve your model, you have to make it available to others. So we don't run production services on our personal machine. So if I have a model that I want people to use, I'm not going to keep it on my personal machine. I'm not going to serve it there. So we need special services for that. And some of them includes the AWS, Google Cloud, Microsoft Azure, and DigitalOcean. So far, I know a lot of people use AWS. So when you save your model, do the flag stuff, then you can put it on AWS, maybe EC2 instance or anything, and then people are able to access it. With that, you have deployed your model. So other approaches for model deployments, TensorFlow has what we call TensorFlow Lite. And then it's just a lightweight alternative to the full TensorFlow. And it's a serverless approach that makes deployment model with AWS and Lambda faster and easier. So if you have some kind of TensorFlow model, it's easier and faster to deploy it on AWS Lambda using the TensorFlow Lite. And then we have the last one, which is complex but powerful. So it's called Kubernetes, and then you can read more about it. This is where I think a lot of people are going now for their model deployment. So the last piece here is how to save your model, and then you can save your model using the name of the network and then .save for the TensorFlow. So with that, it creates a folder in your working directory with this name, SWE prediction DNN, and puts in all the details of your model. So when you want to reuse your model, all you have to do is to do tf.keras.model.load model. With that, you simply load your model and you start applying it. And then for the random forest, you can pickle it. And that is simply what I did here. So you open and give it a name, and then we are saving the binary format. So you can do .bin. You can also save it as .pkl, which is the pickle standard extension, but anyone works. Then WB here means I'm writing, but I'm not just writing as text, I'm writing the binary format. That is what WB is. And then I open the file. I'm gonna dump my model inside of the file and then close that file. So that's what I just did here. And then to load your model, you simply open that file you just created again. But now you are going to read, not write. But you're not just reading, you're reading the binary format. So you read RB and then you pick .load. So I have a very little exercise here. So if you notice here, I selected some very bad combination here. And then for the hyperparameters, it doesn't even match the first performance. So it's just an exercise to get some reasonable values to see if you're able to beat the initial ones. There is no guarantee for that, you just have to try different values. And then some researchers have also proposed some ways to get a better grade, like binary search and other stuff, not binary, like genetic algorithm or something. Yeah, those are better ways to do it. But in the end, you just have to specify some values. So I want to acknowledge HP for allowing me to present this tutorial. And many thanks to eScience Institute and organizing members for allowing me to deploy this. Thank you. So do you have questions? Go ahead.
Back when you were in the neural network, and that picture where you had to go into the lead, and then you show
Okay.
So different functions. What about the way in which those W's go? Is it like standard to make that additive, or is that just like really flexible how those go?
Well, the standard is to make it additive, just as we have it here like a linear regression. That's the standard I know so far. So we make it additive, and then you add the bias term, and then you activate it and send it out to the other connecting node.
And in those, down to the line. Yeah, right there. So is it standard in all of those that are additive, or is one of the changes
Well, this is the standard for feed-forward neural networks, but some of those neural networks, you have to do some little adjustments to it, like the convolution neural network, you have to do some convolution operations and the likes, but the standard for feed-forward is to do the additive stuff. And for most of them, the last layer or before the last layer, you have to do this stuff. Like for the convolution, after the convolution layer, the ReLU and all, you flatten it. And then when you flatten it, you get a dense layer, which is something like the additive before you pass it to the outer layer. Yes.
So it's interesting how the random forest worked better than that. Part of that you said the neural network has to be too.
Yes.
Can you talk just a little bit about what would you do to spin that neural network?
Okay. Yeah, that's a very good question. And then it is also worth noting that at times, neural networks just can't beat random forest no matter what you do. So, but if I will tune the model, there are a lot of different things I could tune. I could add more hidden layers. I could tune the number of nodes in the hidden layers. Then I could regularize, like add some dropouts. I could change the activation function. There's a lot of things. I could change the loss function I used. I could change the learning rates. I could change the optimizer. So we have a lot of options. So there are many things to change. So it's a little bit stressful to train. Yeah. Do you have other questions? Thank you very much.
All right, let's take a 15-minute.